pleasure to introduce Dr. Bradfield Lyon from the International Research Institute for Climate and Society of Columbia University. This is a very well-known institute located in upstate New York, north of the Hudson River. So Bradfield Lyon did his undergraduate work at University of Lowell in Massachusetts, where his major was meteorology, and then for his doctoral studies he went to MIT, where his advisor was Dr. Randy Toll. And Bradfield's doctoral thesis was on analysis and predictability of extreme temperatures in North America. And after his doctoral degree, he taught in colleges in Massachusetts for several years, and he joined IRI, the International Research Institute, where he is now a research scientist. And Bradfield Lyon specializes in analyzing climate data and using GCMs as diagnostics. And he has published several very important papers on drought and drought prediction, not only on this continent, but also in Africa, especially East Africa and South Africa. And he is very active in the meteorological community. He is a member of the Committee on Applied Meteorology in the American Meteorological Society. He is a member of the Drought Working Group in US CLIVAR, and also a similar committee in the World Climate Research Program. So let us welcome Dr. Bradfield Lyon.
Well, thank you very much. It's a very generous welcome. It's good to be here, and there's nothing like having a deluge outside to talk about drought. It's inevitable. So, as mentioned, I've been interested in drought for quite some time, and different aspects of it in terms of looking at diagnostics of the atmospheric circulation and things like that. But we're also interested in, at the IRI, the predictability of drought. The work I've been involved in is on sort of seasonal to interannual timescales, how to predict meteorological drought. So this paper here came out of that work on drought prediction on the seasonal timescale. And basically the idea is that when you're making a prediction of drought, when it's based on an accumulation of precipitation over several months, you can imagine that if you want to make a forecast a few months ahead, you have to know something about the initial condition as well as the forecast. We'll get into that in the talk. So in other words, there's a certain amount of baseline predictability just based on the design of the indicators. As it turns out, if we want to tell how much skill the climate models are giving us in terms of their predictive skill, we have to back out these baseline probabilities to do that. So now if I can pass the first test by clicking this. Okay. So before I even get into that, I think drought, I don't know, it must be something in my makeup or something that it's a particularly interesting problem, but particularly frustrating, because we're talking about quantifying drought. How do you do it? What's a drought? So here I'm showing a picture of severe drought. Matter of fact, this is near record-breaking drought from a few years ago. And you say, right, sure. But the thing is, what we're thinking is that drought, in terms of being interested in it, is we typically think of it as being manifest in terms of its impacts. So it's basically a supply and demand problem, water supply and demand. That you have sufficient water supply to meet the demands of keeping the grass green. And so the answer is, apparently, there's a sufficient water supply here to keep the tree looking fairly healthy. But what's behind the tree here is a body of water. and that's Lake Lanier in Georgia in 2007. So this is the elevation of the lake level, and this is from October to December of 2007, and this is the time that that picture was taken. And this is the lake level, this being the record all-time low of that lake since the 1950s, which is subsequently crossed. So we have a problem here in that when we think of drought, it operates on different time scales. So when we're thinking about hydrologic drought, here's a picture of the reservoir here. You can see it's drained down substantially. That's operating on one sort of characteristic time scale versus the grass can green up rather quickly, for example. This took several months to develop this deficit in the hydrologic sense. So that's an immediate problem we have to face. How do we define our drought? Okay. What makes it a little more complicated in terms of impacts, and I'm not going to talk about impacts today, but speaking of water bodies like Lake Lanier in Georgia, I mean, what's happened is in metro Atlanta region, the population there has blossomed over the last 3 decades. And Lake Lanier actually wasn't totally designed for like be the sole water source for the region, but the demand has gone up increasingly. Here's an example not of Lake Lanier, but talking about non-stationary demand for the Colorado River Basin. So basically what's shown here since the 1920s up to almost the present time, the blue curve shows a 10-year running average of the amount of water available in that basin, and the red line is some estimate of the demand. So demand has been continually increasing to the point where we're almost fully allocated on the Colorado River. It doesn't take much of a drought condition now to stress water resources in a way that they wouldn't have been stressed here because your demand was much lower. Of course, the Colorado is interesting too because in the infinite wisdom of those who were making the water allocations, they defined them during the 1920s here, which happened to be one of the wettest periods in the Colorado River for a few hundred years or something. So they chose the high point to say, well, there's this much water available, and therefore we'll make our allocations based on that. And just to say that there's nothing unique about the Southwest or semi-arid regions. Here's an example from Rockland County, the home of the IRI and Lamont Doherty Earth Observatory, the county where it's located. And they're talking about building a desalination plant because there's not sufficient water resources within Rockland County. Rockland County is separate from the New York City water system there. And at one point I did a little study looking at this because they were saying, well, the most recent droughts during this period here are historical droughts that we've never seen in Rockland County. And I said, well, if we look at the past 100 years or so, we find that deficit averaged over the main drought period here actually isn't all that out of the ordinary. The 1960s drought in the region was in fact the drought of the century. Matter of fact, the last few centuries, as best we can tell from dendrochronology's tree rings. Well, what's happened is, following the major drought here, it's been relatively wet, above average precipitation for the decades following, but the population has been going up steadily. So it's just like the Colorado River Basin. It's a ubiquitous problem that not only that, it's happening everywhere. No. So increasing demand makes your system more sensitive to drought. So when we talk about drought indicators, which I'm going to get into with the bulk of the talk here, I mean, ultimately you want to calibrate those to some sort of impact. It could be water resources or whatever. But that's another topic. So in terms of predicting drought, we have to immediately identify what is it that we want to predict. So again, if drought we think of it being manifest by its impacts, which impacts could be on agriculture, water resources, all kinds of things, and they develop on different time scales. As I mentioned, fundamentally, in terms of impacts, that's the imbalance between water supply and demand, which leads to impacts, and of course, what complicates things are the humans in terms of their demands. But ultimately, it almost necessitates the use of multiple indicators for monitoring drought conditions, and when you're trying to make predictions, you want to make predictions of multiple indicators, because the best one of these indicators depends on what you're interested in. If I'm interested in the agricultural sector, I'm interested in one type of variability on a certain time scale versus, say, water resources. So all those things have to be taken into account. So what I'm going to talk to you today is one example of using multiple indicators looking at meteorological drought, just variations in precipitation. Oh yeah, here's the other, I forgot I put this. This is going back to Georgia. So another complicating factor of the humans. So I'm calling this drought denial, or is it delusion? So you know what this fellow's doing here? Spraying. He's spraying this lawn, which during the 2007 drought, right? It dried out. So somebody's like, well, I don't want a brown lawn, I want a green one, so I'll paint it. So when we talk about impacts, it was actually a positive impact for these guys that would charge, I don't know, several $100s to paint your lawn. And let's see, I think I had a couple of quotes here that, yeah, Tolstoy. It is amazing how complete is the delusion that beauty is goodness. The Kreutzer Sonata, actually, you read that, it doesn't end so well either, about being jealous and jealous of your neighbor's lawn. Or a better quote perhaps is from a current philosopher, if I can get this thing up, Conan O'Brien. When all else fails, there's always delusion. Well, we won't talk about delusion today. Well, maybe we will. I will. Hopefully it won't be too delusional. Okay, so meteorological drought. As it turns out, the biggest driver of impacts is the deficiency of precipitation relative to some climatological average value. Yeah, there are other factors like water loss from the land surface due to evaporation and things like that, but the primary driver is variations in precipitation. So I decided to look at so-called meteorological drought, where I'm only going to look at variations in monthly precipitation and how it gets accumulated over time. So I'm going to emphasize the use of this so-called standardized precipitation index. It's called the SPI. Yeah.
Yeah, the question about that. So what you're saying is, does that actually depend on the time scale? For example, I think a lot of people actually try to emphasize that it's P minus E.
Yeah.
That is actually the primary driver, but maybe is that more relevant for longer time scale rather than sort of the shorter time scale?
Good point. Ultimately, yes, you'd like to have some measure of P minus E. And again, when I'm saying the biggest driver is the precipitation deficit, not E per se. And if you don't have the P, you don't have the E. So, but I think particularly for agricultural drought, the P minus E can be very important. Matter of fact, I'm not going to get into it today, but sometimes we call this thing flash drought. What developed this past summer over the central U.S., you depleted the soil moisture to the point just below the surface that it was dried out. There was some soil moisture near the top layers. But then when we had this meteorological precipitation deficit, that began to dry out the top layer to the point where you basically exhausted that moisture in the top soil layer, that all of a sudden there was no soil moisture at all in that top layer, and you had this rapid response to plants, for example, and also the temperature shot up. So we had very high temperatures in the central part of the U.S. This time of year. So ultimately, yes, this is an approximation to what you really want to measure. Like land surface modelers, they're trying to model all those effects, so P minus E, basically, sort of thing. But it depends what you're looking at. In that case, they may want to look at the soil moisture profile. What I'm saying is this index is a proxy. You could correlate this with soil moisture. Actually, if you look at like a 6-month SPI, correlates very well with, say, the top 40 centimeters of soil moisture typically. This is just a quick summary slide, just trying to get at what's this SPI if you've never seen the thing before. So basically what you do is, for a different accumulation period, say just consider 1 month, the simplest case, you look at the historical record, all these dots, and you look at what was the range of precipitation. In this case, I don't know, 0 to 100 millimeters for some location. You know, what's the probability distribution? Now, like here's the wettest, and here's the driest. And you fit some distribution to the accumulated amount of precipitation, basically. It could be for a month, it could be for 3 months, 6 months. And once you know the probability here, and precipitation typically isn't normally distributed in a Gaussian sense, so it's fit to a distribution that's then transformed to a normal distribution with zero mean and unit variance. So then, in monitoring, for example, if you received whatever 80 millimeters of precipitation, you basically map that onto this index here and say, well, I'm at +1. So this SPI is just a standard normal distribution, so +1 standard deviation. Wetter than average positive, drier than average negative, and obviously nonlinear in that, that if you're at -1 to -2, this is a lot more severe, a shift of 1 unit from here to here versus here to here in terms of severity. So that's the basic idea. Of course, if you're at a value of 0 here, you come up, and that's going to be the median value, 0. I mean, 0 would map onto 0.5 probability, which you could then say is an amount over here, which is the median amount, which is, I don't know, 60 millimeters. So that's kind of in a nutshell the SPI. It just takes the cumulative precipitation, maps it onto a normal distribution. And people assigned severity levels. We're only interested in the negative ones in terms of drought. That, you know, this is moderate drought versus severe versus extreme. Yeah, you could say that in terms of this is less likely from a probabilistic sense, but if you're talking about something being severe, it implies impacts, and ultimately impacts, you have to relate your indicator in some way to, say, agriculture or water resources. But nonetheless, there's the SPI. So here in lies the basic issue. If we say we take the 6-month SPI 6, and we'll say we're evaluating that at this time t. So my boxes here represent monthly precipitation, so P1 to P6. So at time t, I'm looking at what the precipitations occurred over the last 6 months. I fit that to a cumulative distribution, I map it onto a normal distribution, and that's my value of SPI 6. But we see immediately, if I just wanted to know what's the value of this index going to be a month from now, when I know, say, nothing about what the precipitation is going to be a month from now. If I knew nothing about this, I'm still going to have skill in predicting this simply because I know 5 out of the 6 months in my initial condition. So this is sort of the simple math problem that, say I want to use a GCM to predict this precipitation, compute this SPI index, and then I want to correlate this predicted amount to what actually occurred to come up with a model skill. Well, a lot of the model skill is going to come from the fact that you knew a lot about the initial condition, not just the fact that you could have a bad forecast here and still have skill in predicting the SPI. That's the basic idea. Oh, my parenthetical interjection. Redding of white noise. I mean, it's basically the same idea, right? That if you knew nothing, if you had random numbers in my SPI index, it's going to show persistence, even if I know nothing about month-to-month autocorrelation in the time series, precipitation. And you know, this is a common problem just looking at climate time series generally. Here's just take your favorite random number generator. And here I just sampled from a normal distribution. And you put some moving average process through there, and you can convince yourself that, well, this, say we're talking about drought, this is a prolonged drought period, and look at this long-term trend, whereas you can get all this from random numbers. So that's the effect here. It's a very simple baseline that we need to subtract out to get its prediction apart from the GCMs. But as it turns out, it tends to be a pretty high bar to get over. So we'll get to. So my basic approach was this. So I take the observed precipitation, say across the US, and I just use some simple resampling of the monthly precipitation to generate 2 types of time series. So one, I generate monthly precipitation time series with no serial correlation from 1 month to the next. But I don't care about the seasonality of precipitation. In other words, I choose a value totally unrealistically for many locations. I take the precipitation, random year, January 2001. I grab my next random, it doesn't have to be February, my next observation could be, June of 1954. basically all that is a pretty much a random number generator. It's not going to give you anything different than that. It's just going to be a random number generator bounded by the lowest amount of precipitation that was ever observed and the maximum amount. But this is important for kind of thinking about the baseline of the simplest guy. And then the second series, I scramble the data, but in such a way that I don't have any month-to-month correlation, at least by design. But I retain seasonality. So I start with January, my first choice. I chose the data for January 2001. I follow that by a February observation, but it could be for any year. So that way I go through and I generate a time series 100 years long. Matter of fact, I generate 100 of them so I can build up the statistics. Okay. And then I looked at the autocorrelation of the SPI and other indicators to see how they behave based on these two different types of time series. So, as it turns out, if I have no seasonality in precipitation, and I just take my SPI indicator, this meaning 3 months, 6 months, up to 12-month accumulation, and I look at my autocorrelation as a function of lag. Okay. So, obviously, perfectly correlated with self at lag 0. But the decline, sort of the median value here is what's plotted across my 100 time series of what the autocorrelation is. It declines in a very nice linear fashion. In other words, if I get to 12-month SPI here, the red line, at 6 months, my autocorrelation is exactly 0.5. And you can run through this and show yourself how it works mathematically. I mean, people have looked at time series analysis and talked about this some time ago. It's just an application of this to a meteorological drought indicator. But basically, if you have some variance of precipitation sigma, I take some running average, which is sort of like the SPI is doing at 3 months, 6 months, so forth, is n here. You can show mathematically that covariance goes as this, and then the correlation between two adjacent values goes as n minus 1 for an adjacent value divided by n. So in other words, if I had a 3-month SPI indicator, and I had a 1-month lag, that have 3 minus 1 is 2 over 3, it would give me 2/3 correlation. So at 1 month, this would be 0.67. But you see immediately that that's a pretty good amount in this seasonal predictability game. I mean, a lot of times we talk about being interested in correlations that are 0.5 or so. Well, for a 12-month indicator, if I know nothing about the precipitation for the coming 6 months, I can, on average, will get a correlation skill of 0.5. Okay. It turns out there's nothing special about the SPI when you do this. So, for example, I just showed a 3-month moving average of precipitation here, and it autocorrelation declines linearly. 6-month percent of normal, or a percentile. Okay, it's 9 months. It's only the accumulation period that determines the rate of the decline. And if you look at a place like here in New York, which I think is shown here, I average across, say, the state of New York, where there's not much seasonality in precipitation. There's some, but it's fairly flat distribution throughout the year. That, in fact, this is pretty much the autocorrelation that you see in real observations. So these are synthetic time series. This is the actual observations. It also tells you that there must not be much month-to-month correlation in precipitation in New York, which is also true. Okay. I looked at some other indicators. So, for example, if we're looking at something more like P minus E, one of the original sort of simple statistical models to try and model the water balance of the soil layer was this Palmer Drought Severity Index developed by Wayne Palmer, I think back in the 60s. And it has this sort of recursive formula here that the PDSI at some time t just equals a constant times its value was last month, plus this z factor here, which includes the effects of precipitation and temperature, trying to mimic evapotranspiration. But if you think about it, that if we scramble the z-index, which is a monthly input here, which includes the effect of evaporation. If it's random, if there's no serial correlation, you're pretty much just adding noise to this guy here. So that your correlation is just going to go as at time t plus 1, this will become, it's a recursive formula, so it'll become 0.897 squared, and then cubed, and then, so it's just going to decline exponentially. If you actually put in these scrambled time series here, you would in fact find that that's the case. So there's nothing unique about the SPI in doing this sort of thing. What makes things interesting is that when you consider seasonality in precipitation. So again, the time series, this is synthetic data, such that there's no month-to-month autocorrelation in the precipitation values. But there is the annual cycle in precipitation that you would expect to see. So in this case, I've averaged across the state of California. And I've looked at different accumulation periods, 3 to 12 months here. So what's plotted in the dashed line is the linear decay. So my autocorrelation drops to 0 at 3 months for the 3-month SPI, for example. And it drops to 0 at 6 months for SPI 6. So if there was no seasonality in precipitation, we know that there'd be a linear decline in the autocorrelation. What we see is that depending on the start time, so in this case I'm starting at March would be my 0 lag, and then April, May, June, and so forth. The autocorrelation is actually much higher than the linear decrease. Okay? But if I start in October, remember this is California, so March is basically the end of their precipitation season. I mean, the basic intuitive way to think about this is that if you're in drought, say, at the end of the rainy season, you're not going to get out of drought in the dry season, right? You're not going to add any precipitation to relieve you from that. However, say you're in drought at the beginning of the following precipitation season starting in October, you can quickly begin to erase that. So the autocorrelation, in fact, decreases much more rapidly than the linear decrease. So seasonality has a tremendous modulation on the autocorrelation of the indicator. So again, if you're trying to make predictions of the SPI, you have to know what this baseline is for the realistic case of having seasonality in precipitation for each of these start times. Okay. I don't want to spend too much time on this, although it might be somewhat counterintuitive that in the previous example here, I was saying that, well, it's the end of the precipitation season that you're not going to get out of drought in the coming few months if you're already in drought because it's not going to precipitate. So that implies that it's the amount of precipitation that matters. But in actuality, it's the variance of the precipitation that matters mathematically. But for all practical purposes, the two things are highly correlated. In other words, here's the amount of precipitation in inches, and here's the standard deviation across this climate division data for the US. It's a fairly good linear relationship there with a correlation of 0.88, but that's sort of just the detail. But here's the upshot. So yes, we need to compute the baseline skill to evaluate how much additional skill the GCMs are giving us. But there's useful predictive information in our baseline information by itself. And, so a simple way to show that is shown in the paper that I reference is, say for decision-making purposes, we say, well, if I don't have a correlation greater than 0.6, it's tough to take any action on something. I mean, 0.6, I mean, in terms of explained variance in a linear fashion, right, is 0.6 squared, which is only about a third of the variance or something. In other words, the point is, say statistically you could show that you have 100 years of data, that if you have an autocorrelation of something at 0.2 is probably 0.25 or something statistically significant, but it explains 4 or 5% of the variance. I mean, are you going to bet the farm on an indicator that's explaining 5% of the variance? Probably not. You may not bet the farm on this, but at least it's. But the idea here is just to say, what's the number of consecutive months that the autocorrelation, my measure, if you will, of baseline skill, is greater than 0.6. And this is for the SPI3. And you find that there are several places, no, this must be SPI6. Yeah. There are several places where you can actually get, say, 3 months of useful skill from a practical point of view out of this. And of course, if you look at the longer the time scale of accumulation, the more skill you're going to have, right, by the same metric. So the number of months where the autocorrelation is greater than 0.6 for a 12-month SPI, depending on the seasonality of precipitation, you can get 8 or 9 months of skill. This is a very high threshold, as it turns out to be, by including GCMs in the forecast. Conversely, if you know the GCM doesn't have any forecast skill, there's something you can say about the predictability of this. You don't have to just throw up your hands and say, well, we don't know what's going to happen. The models have no skill. Yes, but we know there's going to be autocorrelation from the design of the indicator itself. Okay? This is just saying that the previous chart relates to the seasonality of precipitation. Well, it turns out that if you think about this a little bit more, we can do even better for this baseline case. Again, this is the simplest type of persistence we can imagine, that we have no month-to-month correlation in our precipitation. So these, again, are supposed to be my little schematic for monthly precipitation in the boxes. But let's say we have the SPI 6 at time t is based on the precipitation over the last 6 months to determine the index. And I wanted to make a prediction 3 months into the future. That's SPI 6 at time t plus 3. So I could just correlate, as I did in the previous examples, SPI 6 at time t with SPI 6 at time t plus 3. But if you just look at the little graphic here, you could say, well, if there's no month-to-month autocorrelation, the only skill in this prediction is coming from this part. The common signal, if you will, is all contained here. This is the only known information to both indicators. It's the baseline case. There's no predictability about what's going to happen from one month to the next. So what you're really doing in sort of the standard way of looking at persistence is you're adding noise. Well, adding noise, at least in my life, hasn't been particularly helpful in situations. So I said, well, I'm going to reduce the noise by getting rid of this here and say, my best predictor of SPI 6 at time t plus 3, you can show mathematically is in fact just SPI 3 at time t, because it's the common information. Yeah. So there's the idea. Look at it this way, that if you had a simple regression formula that you wanted to predict SPI 6 at different time leads, right? I just have some coefficient times whatever my predictor is, and I can say what I'm looking for. So at time t plus 1, I'd have some coefficient A1, turns out to be essentially the autocorrelation at 1 month lag, times SPI 5. So you can see what's going to happen sort of geometrically here is that you go to the next month, your best predictor is going to be SPI 4, right, times a new coefficient. So you go through all of them, and you can compute what that future SPI index will be. That's what we call the optimal persistence in this simple baseline case. Again, it's kind of simple and kind of boring, but it's got some interesting consequences, a couple of which aren't intuitive. So number one, say we look at the case of no seasonality in my precipitation. And again, I'm looking at the autocorrelation. My conventional way of looking at autocorrelation with no seasonality in precipitation, we know is going to decrease linearly. In my optimal persistence, I actually get this as my autocorrelation function. So you gain something. This dashed line here is the difference in the autocorrelation. So in this case of no seasonality, maybe you can gain something in the order of 0.2 in terms of correlations. When you add seasonality, it becomes even more dramatic, particularly depending on the time that you start your calculation. So again, in California, starting in March, I can get very high correlations at the end of the precipitation season. I mean, we're talking here at 5 months, getting a correlation of 0.8. 5 months lead time, 0.8 correlation. And if we notice the behavior here, the change in scale is quite impressive. we can have over our standard way of looking at persistence differences on the order of 0.5, 1/4 of the variance, an additional 1/4 of the variance accounted for from the simplest type of autocorrelation you can imagine. As it turns out, when you get into the beginning of the precipitation season, we know that seasonality can reduce the autocorrelation, and our optimal persistence method doesn't bias much in that case. But it's kind of interesting that, okay, this is good, and if you're interested in forecast skill by this simple method, this gives us something very useful. But there's a couple aspects of this that may not be intuitive when we think about a persistence forecast. So one is that the change in forecast skill by this methodology can actually increase at longer lead time. Usually you think of forecast skill as deteriorating with lead time. It can actually increase, and that's what you're seeing here, right? That the difference is actually increasing with lead time. Not so much depending on the time of year, but in the nose seasonality case, for example, it does. And another non-intuitive result is that you can actually get an amplification of the initial condition in this methodology. In other words, again, when we think of a persistence forecast, we think, well, the value is, -2 to start with, and at 1 month it goes to -1.8, and it just declines. But in this case, you can actually get an increase. So for example, here's a recent example of the 3-month SPI at the end of November 2012. Okay. Negative values here in the warmer colors. Here's what was observed for the 1-month SPI in November 2012. It was very dry in parts of the Ohio Valley up here into actually New York and New England. So if I'm trying to make a forecast of this, it's going to weigh on this forecast value more the farther ahead I move in time. So in other words, here's my baseline forecast for December, given my initial condition, based on the SPI 2. If I go ahead an extra month, I want to make a forecast for January, it's going to be based only on my 1-month indicator. So my signal starts off relatively weak, and it can actually increase as my best estimate of what's going to happen. So my baseline case here, it's actually more flexible in some ways than the indicator itself, if you get what I mean. It's very, say you have a 6-month accumulation period of precipitation. It's fairly slow to typically move that index around. But the best information I have in this case, if it's only the last month, well, that's the best information I have. So some additional forecast skill there. Finally, without getting into the mathematics of it, we can determine the full PDF of what our future probability distribution will be for my indicator. So basically, everything's nice and Gaussian. So I have a normal distribution where I have 2 parameters, basically the mean and the variance. I can determine the full distribution. So I determine my forecast mean, I think in the simplest case of the simple regression. And my forecast standard deviation is basically the observed deviation, which in the case of the SPI is defined to be just unity, times the square root of 1 minus this autocorrelation squared. Okay. So then you just have standard things you can do with a Gaussian distribution. You can look at the probability of the future value being below some user selected value, say, of the index. Or you could turn the whole thing around, basically solve this equation for x and come up with, plug in a probability and I'll tell you what, the value of x will be associated. So here's an example. I guess this one's from the paper. That here's the observed SPI 12 in April of 2011. We had a major drought going on in the southern U.S. Into Mexico. Okay. So in terms of my baseline predictions, I can do different things. I could say, for example, I want to know what's going to go on in July, the end of July, given my start time of the end of April. And so I want to say, well, what's the probability of my indicator being less than -1? Nothing special about -1, choose any value you want. And I can quantify what that probability will be. If I'm here in eastern Texas, I'd say, well, the odds are pretty high 0.8 or 9 or something, that I will be below that threshold 3 months from now. Or I could say, well, what's my best estimate of what the forecast value will be itself? In other words, predict X. So this would be my best estimate forecast. And this is what was actually observed in July 2012. So you notice immediately that the patterns are quite similar between what was actually observed, and you think about the probability of being below a certain threshold, or, I mean, it's weaker, because in this method, you typically don't get amplification. It's possible, but we did not here. But that itself provides some very practical forecast information. So for example, during this drought, people in this part of the world actually wanted to see the results of these tools, just to say, well, what is the probability that I'll still be below some threshold? So from an applications point of view, sometimes decisions are made, for better or for worse, on trigger values. If some index drops below a certain threshold, it's codified that then I take action. Water restrictions kick in, things like that. This is a way of telling you what's the probability you're going to be above or below that threshold to make a decision. Okay. And actually, you can get these tools online. Here's the link here. You can email me and I can send it to you directly. Let's say, for example, here's the current condition of January, the end of January 2013. Of course, the drought in the central part of the United States has been there for some time. We can look at what's the future of this drought going to be based, say, only on the persistence method. I can choose multiple indicators with this tool here, and in this case, I'm plotting the actual best estimate of the SPI value. It's a forecast made for the end of April 2013, given the conditions at the end of January. So we see that it's persisting here, particularly in the upper plains, with a fairly high probability if we look at it in terms of, instead of the best estimate value, we can look at select a threshold. I just happen to choose -1. There's a whole list there you can choose from. Very high probability it's going to persist. It turns out if you include the IRI's multi-model GCM seasonal forecast of precipitation, this is what the probability would look like. The exact same forecast 3 months from now versus the simple persistence method. So there's persistence, there's with the model, persistence with model. The model, the combined models don't really buy much. I mean, it's a little deceiving in that these are discrete values, it's not continuous. You'd like to see an actual difference map. But most of the predictability is coming from the initial condition in our optimal persistence method here. So finally, we're expanding this to look at, the IRI is the International Research Institute. They're working in different parts of the world to look at the predictability of drought in different regions. And here's just a map showing, my metric, saying where's my correlation skill, the number of months that it exceeds 0.6. Okay. So here's the December start time. But in this case, I'm not using synthetic data. I'm using the actual observations, which may have month-to-month correlation, which is only going to enhance your baseline skill. So I can get several parts of the globe with 4 months of skill exceeding 0.6 for my optimal persistence method. And of course, there's a lot of geographical variation, which is of interest. If I'm in the US, I don't want to know what some countrywide average value is, and if I'm here in the Southwest versus in the Northeast, I want to know the difference. We can quantify that. And we've done this for different times a year, and now we're just going to include the GCM forecast with it. So basically, what we've done is we've quantified these inherent persistence characteristics, focusing mainly on this SPI, but you could do this with any meteorological drought indicator, which could include ones that, like PDSI, which include P minus E, which would be a more realistic indicator. We saw the effect of seasonality in precipitation, and as it turns out, it's the seasonality and the variance of monthly precipitation that can considerably alter the persistence characteristics from the case of no seasonality, where we had the simple linear decay. We saw that we could greatly enhance our autocorrelation, or decreasing, depending on where we are in the annual cycle. And we further eked out some skill by using this so-called optimal persistence case. It's only optimal in the sense of this baseline case. You can do better than this by including other predictors, say something based on ENSO, or just the autocorrelation of actual observations. But the upshot is you can generate the full PDF of these indicators, and in addition to providing a baseline to compare with the GCMs, it's a very useful tool in its own right. I mean, that last graph I showed, well, the third graph from the end, the IRI multi-model forecast included in the forecast versus the optimal persistence. Very, very simple. So the bulk of your skill is in fact coming from the initial condition. And that's a very useful tool in cases where A, you don't have any model at all, and B, even if you do, there's no skill in its seasonal precipitation predictions. So I guess I'll leave it there. Thank you very much.
Questions for Brad, please? Yes, Margaret.
Isn't the illustration you did on using the models to predict the drought in the middle of the U.S.,
Right.
since I think I'm right in this, that most of the rainfall there during the summer falls as a function of these propagating squall lines, which aren't resolved at all in the models.
Right.
So you wouldn't expect the models to be able to do a job on something they just can't do.
Yeah.
You know what I mean?
No, that's exactly the.
But there is parameterized preference, so I think models do have a.
No, but that's a Mesa scale organization, which the present climate models don't have that capability, is my understanding.
Yeah, another way of looking at that is if you look at the spatial correlation
Yeah.
in precipitation. So I've looked at this sort of thing depending on time of year. So yeah, it's particularly as you get in the spring towards summer, yeah, it's going to be a lot more convective. So sort of the spatial decorrelation distance decreases a lot in the summertime because it's convective things. You get these mesoscale.
Yeah.
And then when you have these larger synoptic disturbances, like it's passing by us today, well, it's got a nice broad structure. You get a bigger auto. So that's one of the biggest problems, challenges in this drought prediction business is in the summertime, because that's when we're growing crops and things like that. And that's where the models really aren't giving us much. And so, but I'm saying through this method, even though it's not rocket science, it's climate science.
Yeah.
I don't know, climate's rockets. I'm a climate guy. I think they're equal. But it's very useful skill that you can do. You don't have to throw up your hand and say, we have no idea what it's going to do the next 2 months. Well, this integrated amount, to the extent that you can correlate this to what's something real on the ground, I think I threw on a slide here. That's my cue here. Supplemental slides. We did this in Sri Lanka just quickly. So there's a lot of variation in rainfall across Sri Lanka. So the idea is to say, hey, in the agricultural sector, what's the best drought indicator to use? So we basically correlated a whole bunch of different drought indicators with payouts to the farm industry. Now there's all kinds of political considerations there that might cloud things up. So we're like, we know that. But we had 40 years of pretty good data, and they're actually pretty reliable, as it turns out, in terms of their consistency. And so we actually found that we could correlate what's the best indicator of when we think there would be a payout. So you could actually calibrate your index to something. So this is a crude way of just doing it. This is the climate guy's approach to the problem. But we could, you can compute all kinds of statistics, your hit rates and so on. But that's the useful bit. You need to say which indicator is most closely associated with crop yields or that sort of thing. And you can try and quantify that. And it's probabilistic by nature, but nonetheless, it's better than just throwing it there.
Sure.
Yeah, sort of a related question, but I don't know whether you've looked at it. So have you looked at the model to see whether they have sort of predictive skill in terms of sort of the 1 month index? So the 1 month index definitely doesn't have sort of this memory type of thing, but
right.
If you look at the model, do they actually have skill in predicting 1 month precipitation?
Well, the companion paper to this baseline probability, because that whole idea, again, was to say we need to figure out what this baseline skill is so we can subtract it out to see what we're gaining from the models. So with the models, we said, okay, we're going to do three things. We'll say what additional skill do we get when we include in the model just sea surface temperature conditions. We don't know anything about the initial atmospheric condition. We don't know anything about the initial land surface condition, which in summertime could be important. So we run the model and we find kind of the classic ENSO sort of signal, like the southern tier of the United States, there's some predictability because it's winter time, you get this subtropical jet coming around. If we include like the initial atmospheric condition and land surface condition, then you get something on the shorter time scales, maybe on the order of a month, where you can show some slightly enhanced skill depending on where you are. I mean, the people who have looked at this in a more rigorous fashion, sort of using state-of-the-art land surface models, they kind of take them offline, force them with the best meteorological observations, then put them back in to force the atmospheric model. They find something basically similar. I mean, the Randy Coster et al., the Lassay experiments. That maybe for a month and a half, it gains you some predictability in both temperature and somewhat precipitation, depending on what part of the country you're looking at.
Yes, Michael.
You might take your skills and peddle them in Australia. I was speaking to my sister last night who lives in Queensland, eastern state, and they've gone from this long drought with record high temperatures where they might have seen on the news they had to add a new color bar to the temperature maps, but now they're suffering from torrential rains. It's rained every day since the beginning of January, apparently.
Mm-hmm.
And what's going on there? What can I tell her?
What do they call it? The big dry in Australia? Yeah, so the thing is, I was playing with some diagnostics that relate to East Africa. And I found that there's some, it's well known that there's sort of lower frequency decadal type variability in the Pacific. So I was looking at that and actually found there's good, both from an observational sort of diagnostic point of view, of a relationship of what goes on in the Pacific and what goes on in East Africa. But then we took a model, a GCM, and forced it to say with only tropical Pacific SSTs. And we got a lot of the same precipitation features. But what I found interesting was Australia was that this shift is around the time of 1998-99. And Australia was, Eastern Australia, or particularly Southeastern Australia, was dry during that post-99 period until recently. But the thing is, it was a little bit dry ahead of that time. There wasn't like this distinct decadal cutoff. But what I found, there was sort of the suggestion of this wave train that was propagating out of the Western Pacific, which could be affecting Australia. But then, yeah, it was only a few days ago that I saw this headline about, being inundated in Eastern Australia. It's like, well, there's the joys of being the climate scientist saying, I think I have an idea what's, leading to that drought. And, it's like, drought, we're inundated. So I don't have I haven't looked at in detail what, the synoptics of the most recent situation are. But it reminds me of in New York, we were in a very bad drought in 1999. And I did all the math, and said, well, the odds of getting out of this drought in the coming 2 months are, it's 2%. And then Hurricane Floyd came along and dropped like a foot of rain, which pretty much annihilated the drought. But there was a 2% chance that could happen.
It's a little off topic, but not completely. And that is, in meteorology, if you predicted weather, you tend to, if you take the average of a number of different forecasts, you tend to get the best forecast. Is the same thing true for climate forecasts, with climate models? I don't know the answer.
Right. So what's typically done is, like in the IRI multi-model ensemble, people who have played with this more than I have found that obviously you're going to do some kind of bias correction in the model to make it match up with observations. You have some amplitude bias and stuff. You deal with that. But in terms of the most skill you can get, one approach was to take this Bayesian approach where you say, well, we're going to weigh each model based on its prior performance, in the classic Bayesian prior sense. But they found that you don't really eke out that much more skill, and if you just took the bias-corrected multi-ensemble average of each model and then average those models together, actually give you the best skill. There's some interest now in saying, are there forecasts of opportunity? Meaning, can we forecast something about, can we predict the predictability? You know, like this last year, this drought's rapid onset. Could we say that that was more likely than we would typically say? Okay, there was kind of La Nina-ish going on, but was there something about this that the spread in the models was, and people have looked at that more than I have and found that there's kind of a weak relationship between the spread in the model forecast versus the shift in the mean of the forecast. So there's a subtle bit there that if you have a really strong signal, maybe you're collapsing your PDF a little bit. In my case here, the higher the skill, yes, you're collapsing the spread, but that spread stays the same for every individual forecast. I'm taking this sort of global view of predictability. The question is, for a forecast for this year, is there something special about it that you can actually shrink the variance and have more certainty in it? Something actually Tony Barnston and I are playing with at the IRI a little bit, but again, there seems to be a weak connection there, but nothing very strong.
Yes, I think that.
I read a paper that PDO and AMO also influenced the U.S. drought. Do you think inclusion of the low frequency climate variability will improve your baseline prediction?
Well, in terms of baseline, sure. In other words, that's why I put my optimal persistence in quotes. It's only optimal in my, I call it sometimes, I'm trying not to say it, but it's obvious. It's dumb persistence, right? I mean, I'm taking a random number generator and saying, you know, these are the characteristics. What's the most I can get out of random numbers? And this is the best you can do. But you can further optimize it, exactly. You can condition it on various ocean states. Could be on different time scales. Could be the ENSO time scale. For example, studies in the US and elsewhere, parts of Mexico, depending where you are, north versus south. I mean, a negative PDO and a positive AMO or warm Atlantic, cold Pacific seems to be cases that are favorable for drought. And this has been shown in modeling studies as well as observations. So yeah, there are more sophisticated, much more sophisticated ways you can actually improve upon this baseline skill. But it's not particularly a sexy topic. I mean, it's, you know, what catches people attention to this method is the high bar that you set. When I talk to the people who spend more time running models than I do, or I don't run models at all, but I use model data, they say, wow, that's a, you know, if I look at an SPI 6 and I can get 4 months of correlation skill about 0.6, that's much better than your typical GCM can. Sure. So it still sets a very high bar, and I think statistically you could even improve upon that. And personally, I think that's worth doing if ultimately you're looking at forecast skill. We have to admit, the models can pick up on certain aspects of the climate system. So we don't have to throw up our hands because our models, you know, let's do the best we can with a combined set of tools. That's our take at the IRIs.
Just a sort of a policy question, not related to the main thing. But you said at the beginning of your talk about Rockland County, and you're putting in a desalinization plant. Presumably they would take the water out of the Hudson River.
See, that's a problem.
And that's going to be very expensive, right? And especially during periods of drought, the river's going to get more saline, so it's going to be a non-linear cost of doing it. And that reminded me, like New York City uses about 1.5 billion gallons of water a day, and there's, I'm sure you know all this, but there's one giant pipe, and it's leaking terribly, and there's something like, there's a 400 million gallons a day or something is lost underground, and they don't know where it is leaking because they cannot turn the water off to the city.
Right.
And for the last 35 years, they've been building a new parallel tunnel, which is finished or nearly finished. So they shut the water off and find the leak, but maybe Rockland County could buy some of that 400 million gallons. They're not going to be losing and save themselves billions of dollars in desalinization.
Yeah, there's been some kind of creative ways and some creative accounting. Just doesn't apply to Wall Street. I mean, some of the water resource ways of calculating things, they're saying, well, we have this sewage treatment plant that we kind of treat the water and we throw it back in the river. Well, we don't have to throw that back in the river, we could use it. But the way you do the math, it's like you only need it during the drought. But if you just accumulate how much water you're throwing into the river after it's been treated at the waste treatment plant, it's a lot of water. But you're not going to have it during the drought. Right. So that's the whole thing with the desalination, extremely expensive. Number two, exactly what you're saying. I mean, the Hudson River, the salt front, moves miles up stream. Matter of fact, the whole tidal influence, you can reverse that. You know, what's the original native people said, well, the river that runs both ways, the tidal influence can actually, you know, reverse it. And on top of it, you have Stony Point, you know, a nuclear reactor upstream. And so if you have like these reverse osmosis filters and things that you're trying to use to take out the salt, I mean, radioactive stuff doesn't care about that, it goes right. So there's a whole set of it and just the cost. But there's recently a study saying that, well, our groundwater supplies don't look as bleak as we thought they were in Rockland County, because they rely about, roughly speaking, like 2/3 of their water comes from underground. They're saying, we thought that whole resource was tapped out, turns out it's not. But this headline I showed you was just from October of 2012, but they're still moving ahead with the desalination. I mean, I've done the calculation. It's how creative you are. And in times of plenty, yes, there's water, but it doesn't take much of a departure from the average climatological condition to put you into trouble. And these wells, basically what happens is they run out of water. They hit the water table and they have to shut them down. And that takes your water offline. So yeah, and I don't even know it in terms of, there's not much interaction between Rockland County and the bigger New York water systems. But the whole thing about leaking water pipes, they're saying that in Rockland County, like, well, we don't want to fix the leaks because that water is going into the ground and we're sucking most of our water out of the ground. But that's a common problem in many parts of the world, actually, the whole leakage problem.
Let us thank our speaker.